So now we're going to build up to the next bonding theory. So we first started off with Lewis dot structures. That was a theory. It's good, not good enough because it really deals with 2D space. Now we got into Vesper theory, which again is pretty good, but it doesn't completely explain how we get different shapes, especially regarding our atomic orbitals that you all learned when you studied quantum. And that goes with like our s orbitals, our p orbitals, and that kind of thing. So with valence bond theory, it says that when we have electrons from two different atoms, when they start to overlap or occupy the same space, that's when we have a bond. So when we have that orbital overlap. When we share the space, so we can see here we have two of our 1s orbitals for hydrogen. They are on their own. Well, actually, we'll come down here. When they're far apart, they have no energy, like a repulsion or attraction. As they get closer and closer, their orbitals start to overlap, and the electrons start to come closer together, and that's where we get that sharing. When that sharing happens, and we get specifically of opposite spun electrons, we get a covalent bond. What we think of as our sharing. So you'll notice here, we have, in our nucleus, we have protons, and then those are going to repel each other. Our electrons are going to repel. But what we do also get is the attractive force between like one electron and one of the nuclei protons. So we'll have kind of this battle or conflicting forces between attraction from the nucleus and electrons from opposite atoms, and also the repulsions between the electrons and the nuclei. So as we bring them closer together, we overall start to see this energy drop, and that is due to the attractive forces. So we're minimizing energy, and that is a really stable, we're increasing our stability. So now instead of just having single electron or atom out in space, they're getting closer together, getting more stable, until we reach this point where we hit the minimum. As we continue to bring them closer together, now we're pushing those nuclei close together, those positive forces, and they don't like that, so our energy shoots up, and that's where we're now becoming unstable. So this minimum down here, this is where we have this optimum attraction. We've increased our attraction, maximized that, and minimized our repulsions. So we have that electron-electron repulsion minimized, and our electron nucleus attraction maximized. So you can see over on the side we have those two 1s orbitals overlapping. We can have a 1s orbital with a p orbital overlapping, one of those p lobes. We could also have two different p orbitals overlapping, and as long as we get that overlap, that's where that single covalent bond comes from. But where does this kind of not work? So we know that, so we need to actually review a little bit. Remember that one s orbital, or s orbitals look like little circles. So if with hydrogen we just have one and it has a single electron in it. With carbon, if we draw its valence shell, the orbital diagrams, we'll see that it's 2s2, 2p2. So when we draw that, we get the 2s2, and then we have our 3p orbitals, and we fill those up. So we have 4 valence electrons, fill those s orbitals, and then the p orbitals. So it looks like from carbon that there's really only 2 electrons available to do our bonding because our s orbitals are already filled. So it looks like we should only be able to bond with carbon twice. And if you remember, we just draw carbon's orbitals. We have the s orbital here in the middle. And I'll switch colors so you can see the p orbitals. Here's one p orbital. Here's another p orbital. And then we also have one coming in and out of the page, but that's one's unoccupied right there. Okay, so it looks like we have our s orbital here is filled. so it's not going to do any bonding. And then we have orbital or electron here and electron here, and each of those p orbitals. Now hydrogen comes along, and each hydrogen has a 1s. So it looks like we should only be able to bond a hydrogen to this one, that p orbital, and a hydrogen here, giving us our covalent, our shared electrons. So it looks like what we should get is the carbon only forming CH2 with a 90-degree angle. But we've seen, and you've seen a lot, especially in our last lesson, that what we really get is carbon is able to bond with 4 things, and it likes 4 bonds. And so in the case where it has 4 electrons that it can share with, it's going to produce a tetrahedral shape. So valence bond theory and atomic orbitals don't really alone explain how we get our tetrahedral shape. So what we want to do now, and the theory that helps us get to the next step of understanding what we are observing in real life, is this hybrid orbital theory, where what we get is a mixing of our atomic orbitals to form these hybrid orbitals. And when we mix our atomic orbitals together, we get brand new orbitals, and they all have equal energy. So before, when we had the s orbitals and then the p orbitals, like up here in our atomic orbital, we filled up the s because it had lower energy, and then we filled up the p orbitals, and then all the p orbitals had the same energy level, which is why we could equally fill them. But our s orbitals didn't. They were on a lower energy. But now what we're going to do is mix all of our valence orbitals together, and now they'll all have their own energy. So what we get is when we mix 2 orbitals together, then we're going to get 2 orbitals. When we mix 3 orbitals together, out come 3 hybrid orbitals, and carrying on for as many as we can get. So what we're going to start with is when we have 4 electron domains, and we are familiar with this being tetrahedral geometry with 109.5 degree angles. So what happens is we take, for example, carbon, which has the 2s and then the 2p orbitals here, the 3 of them. And what we do is, to get our 4 orbitals or 4 electron domains, we take all 4 of these atomic orbitals and we mix them together. So we take an s orbital and we take our 3 p orbitals and put them all together, and then we get what's called as an sp3 orbitals out. And there's 4 of them, 1 s and then 3 p's. So you count them all up based on kind of the superscript here. So 1 s and 3 p's, so we have 4 orbitals come out. And if we this single guy here is one of the sp3 orbitals. We have another one here, another one here, and another one here. So look at when we put them all together, they kind of look like p orbitals on their own, but they're not symmetric. They're kind of like lopsided, like little balloons that we tied at the bottom. So if we were to tie all of our little balloons together, they would look like a tetrahedral shape. But now all of them have equal energy. So now we take the carbon, which had 4 electrons, and we put all of those orbitals together. Well, now we can fit all 4 electrons into each of these sp3 orbitals, and we get 4 bonds that can be made with carbon. So here we can see with methane, each of those sp3 orbitals here, there's 1, 2, 3, 4, has a single electron in it, and then hydrogen's s orbital can now come along and bond, and now here's that overlap. We have one of our covalent bonds. We could also do that with lone pairs. So for example, nitrogen is very similar. So nitrogen would also have sp3 hybridization, and we'll have 5 electrons. So 1, 2, 3, 4, 5. So now this guy is that lone pair right here, and then each of these unpaired electrons in our other 3 sp3 orbitals are able to do the single bond here with hydrogen. So the big takeaway here, like there's a lot of mixing going on and sometimes it feels a little unfamiliar, but the big takeaway is when we have 4 electron domains or a tetrahedral geometry, we're going to have sp3 with a little superscript for the 3 hybridization. Okay, that's the takeaway. Now moving on to 3 electron domains. So in this case, what we're going to do is we're going to take one of the s orbitals and 2 p orbitals, mix them together to get 3 hybridized orbitals. But notice one of the p orbitals is left out. Now it's going to have a very special role soon that we're going to talk about. But the main thing is with this, now we have 3 orbitals. Now they can, so the 1s and then the 2 p's go in, they mix together, and they make this, when we put those 3 together, the optimum shape is that trigonoplanar. So with 3 electron domains, trigonoplanar, 1s and 2 p's go in, so we call it sp2 hybridization. So we're going to be able to use these hybridized orbitals here, the sp2 hybridized orbitals, to make sigma bonds. So those are single bonds. I'm going to talk about it on the next slide. And then these p orbitals are going to have a very special place, forming pi bonds. And then also I just kind of want to explain how this orbital stuff all works. Like how do we mix these together and we get this like unequal dumbbell looking guy. So I'm not sure if you remember this, but our p orbitals, our orbitals have signs. So this, when we have an s orbital, it's all symmetric. There's no little node in it at all. And so we would just say that the s orbital is a positive. Think of like a sine wave kind of, or one part of a sine wave. And then with our p orbitals, we have a node. So we have a positive side and a negative side. And so what we get here is something that looks like that when we mix them together. So if we were to add, I should actually probably draw it a little better. Let me draw like this. So there's my s. Here's my p. So I have my positive s orbital, then I have a positive p and a negative p side. So if I add them together, I get, let me do another color. I get positive plus a positive is very positive. Positive plus a negative, in this case, it's just going to be a little bit negative. So that's where we get this big lobe here and then a little lobe here due to that opposite sign mixing. So now, what does those sigma bonds and pi bonds mean that I was talking about a little earlier? So the general definition is that a sigma bond, which uses a little sigma sign, this happens when we have our orbitals connecting along their axis. So basically what I think of this is end-to-end overlap. So we're going direct overlap. They're connecting completely over. This can happen with atomic orbitals like we saw on the very first slide. This could happen with hybrid orbitals, so we can have hybridized orbitals overlapping from different atoms. I could also have an unhybridized, so atomic orbital and a hybridized orbital. So I can have, like we saw earlier, an sp3 with carbon, and it had an electron in it, and we saw an s orbital from hydrogen. So, whoops. So that would be, because it's direct overlap, we have a sigma bond here. Now, and so we think of our first bond, our first connection, our sigma bond. So we think of that as that first single bond that gets formed. Oops. Now, any additional bonds that happen, these are going to be pi bonds. Whoops. Wow. And we use a little pi symbol, like good math. So this, and hopefully it's easy, sigma starts with an S, and so does single bond, pi bond. It gets used with a p orbital, so this is where hopefully the pi makes sense, so the p orbital. To make these, we have to have p orbitals that were not involved in hybridization, so they didn't get used up in the mixing. So before with the sp2 on the last slide, I said that p orbital has a very special job because it didn't get used up, so now it's available to do some pi bonding. So this is specifically double, could be double or triple bonds. Okay, so what this looks like is side-by-side overlap. So instead of direct overlap, like end to end, this is side-by-side. So what we get is we have one of the, so here's an atom, and it has an extra p orbital left over after it got hybridized. So here's a full p orbital, that full, both sides of the lobe. And then on a neighboring atom, it also has a p orbital that didn't get used. So what they can do is they're really close to each other, so they can kind of reach over and hold hands, kind of. And that's what I think of as that. It kind of looks like a little donut. They're reaching over, and that helps to strengthen the overall connection, these pi bonds, which is why we think of double and triple bonds as being stronger than just a single bond on its own, but it helps to strengthen. But overall, sigma bonds, that first connection, they are stronger than pi bonds because they have a bigger direct overlap, and it's not kind of this like reaching overlap, it's really strong. But pi bonds help to strengthen. But if we just looked at, here's a sigma bond on its own, here's a pi bond on its own, sigma is stronger. But we would never form a pi bond without first forming a sigma bond. So if we look at this, here we have our sp3, the S and all the of the three P's got hybridized and mixed together. 4 go in and 4 come out. So each of these is called sp3 orbital. And we can distribute our electrons through all of them evenly because they have the same energy. With our sp2, one of the S's and 2 of the P's go in, so they make 3 go in, so 3 sp2's come out, and then 1 p orbital didn't get used up, so it's our unhybridized p orbital. And so we have our hybridized orbitals here, and then our p orbital, it's hard to draw. Let me try it with with red. What we'll see with our p orbitals is the one that didn't get used is coming out of the board and into the board. So one lobe coming out, one lobe coming in. So that's where our pi bond or p orbital is and where our pi bond could form. Okay, our next one is 2 electron domains. So this is where we saw linear, 180 degrees. This is called, with this one, we have an s orbital go in and a p orbital go in. And then two orbitals go in, just one of the p's and one s, and then 2 orbitals come out, and we call those sp because 1 s and 1 p went in. So now we get that s orbital, the p orbital, and what we get is an sp here and an sp here. And if we put them together, we get one of those and one of those. And we typically just draw it like that, even though there's technically a little tiny bulb crossover there. So that's our SP, so it's 180 degrees, just like we did before. So we're going to be using our hybrid orbitals here. So these guys, hybrid orbitals for our sigma bonds, and then our p orbitals, our unhybridized p orbitals, get used for our pi bonds. So with sp, so linear, we could make 2 double bonds, so one from here and one from here. If we had, let's say here's our connections, we could have, here's our central atom that is sp orbital, so we can make our single bonds to each one from our 2 SPs here. So that's our linear. And then it can make a double bond either with 2 of them, or it can make a triple bond. So those 2 p orbitals could either be split between 2 different atoms, or it could go all with one, just depending on our connections and the electron or the atoms that are connected to it. So big takeaway with this one is linear is an provides sp orbitals. So how would we draw this? I'm going to try my best to draw it. I'm not the best artist, but let's look at what's going on here. So I have carbon and carbon. So I'm going to first identify on this carbon how many connections does it have. So it has 2 electron domains, which means that it is linear. So we know that 2 electron domains are linear, means it is sp hybridized. And this carbon here is similar, so it is also sp hybridized. So let's draw those carbons. There's one carbon. Maybe I'll write 1 carbon. Here's another carbon. Now, terminal atoms don't do hybridization because they don't have more than one thing to connect to. So with our hydrogens here, they're just going to have s orbitals. I forget what color they called it. We'll just say they each have a 1s1. So just 1s orbitals with 1 electron in them. So in order to keep with the theme, I will try to color code. So first let's draw our hybridized orbitals for each carbon. We have sps, so we're going to draw those like that. Here's one sp, here's another sp for that carbon. And each of those guys has 1 electron in it. And then this other one on the right has 1 electron in it. We'll do them spin down, but just as long as they're opposite of the other thing. Okay, so now let's think about what's left over for our carbon. So our carbon has a p orbital coming up and down, and also one coming in and out of the page. So this is my attempt at 3 dimensions. Same thing here, up and down and in and out. So let's actually draw our carbon has the 2 of the sp orbitals, and then it has 2 p orbitals left over. So carbon has 1, 2, 3, 4. Okay, cool. So we're trying to maximize bonding. So if we were to fill up our sp orbitals, then they wouldn't be able to bond. So we'll spread out those electrons. So we have, we put the sps in, so now we'll put the p electrons in. And then this one will do a down and a down. Cool, so what that means is we have opposite electrons, so they're going to connect on the top and bottom. There's one bond, one of our pi bonds, and then they're going to connect from the front to back. So there's another pi bond. I'll actually draw it. So here we have a pi bond, a sigma bond. And now with our hydrogen is right here. It has an s orbital for our hydrogen, and it's going to have opposite spin. So we have sigma bonds there with that overlap. So we can see here's our sigma bonds with those direct overlap, and then here's our pi bonds. 1 pi bond and a second pi bond. So kind of messy. Now how I would designate these is I would literally label pi bond between, pi bond colon between the carbon p orbital and another carbon p orbital. Same thing here. So there's a pi bond between one carbon's p orbital and another carbon's p orbital. Now with this sigma bond, I would say sigma between the carbon's sp orbital and the hydrogen's s orbital. So we're just kind of helping to label so it's clear what's going on, especially when our art skills, i.e. me, is not maybe the strongest. So with this carbon here, we have a direct overlap sigma bond between one carbon's sp orbital and another carbon's sp orbital. And then this sigma bond over here will be the same as what we had right here. Now moving on, 5 electron domain geometry. This is where it gets a little bit more kind of questionable in the science, whether this actually happens or not, and there's disputes, but for now we're going to teach it. So when we have 5 electron domains, this is called sp3d. So basically what we think is happening is that we have an s orbital, the p orbitals, the 3 of them, and then now we're tapping into the d orbitals. So we'll use a d orbital to give us our 5 hybrid orbitals, so 1 from s, 3 from the p's, and 1 from the d's. And now these unhybridized d orbitals could theoretically give us pi bonds if possible, but we're not really going to see this. So we'll use those d orbitals to make the pi bonds. So we won't be able to have expanded octets on things that are in the 2s shell. So for example, if our valence shell is anywhere in that second row, so carbon, nitrogen, fluorine, all those, because we don't have a 2D set of orbitals. There's no elements in there and no 2D, so we won't be able to have expanded octets if our central atom is in the n=2 shell. Similarly, for octahedral, now we have sp3d2, so we're tapping in 2 of the d orbitals to give us 6 hybridized orbitals. Now this has a really long name. When we say each of these orbitals is called sp3d2. And so what happens with this is our octahedral geometry is into account. Now this could either be any of our moleculars with those 90-degree bond angles. So similarly, we'll be able to use, in theory, our d orbitals to make the pi bonds. Here is a chart that has a summary of these with those electron geometries and hybridizations. So in order to practice, we're going to just look at our electron domains for all of our examples and figure out what they are. So I've gone through and went back to all of the practice problems and figured out how many electron domains. So with the 3 electron domains, we had trigonal planar, so we have 3, so we're going to have s providing 1 orbital and p2. So s and 2 p's come in to make that hybridized orbitals of 3 sp2 orbitals. For 4 electron domains here, so we would again draw the Lewis structure, count those domains. We have 4, so we need 4 total orbitals going in. So we're gonna have s and then 3 p's, giving us 4 sp3 orbitals. Same thing is gonna be for our selenium chloride, and then carbonate is gonna be sp2 due to those 3 electron domains. With 5, we're going to have 4 coming from S and 3 P's, and then now we need to tap into 1D. So both sulfur tetrafluoride and bromine trifluoride will be sp3D. And then for 6 electron domains, we need the S's, all 3 P's, and now 2 D's in order to make that those 6 electron domains. So hopefully that is kind of clear. So the only additional thing is in that big old chart that we made, now adding under each of those electron domains the hybridization of those central atoms. So sp, sp2, sp3, sp3d, and sp3d2. And along with that, considering when can we have pi bonds, and as far as you all are concerned, those pi bonds come in when we have sp or sp2 because we didn't hybridize a p orbital.